Okay, hello everyone. My name is Saba and I'm a researcher at the BIOMATH group. We are in the Department of Data Analysis and Mathematical Modeling of Ghent University. And today I'm going to share with you the latest results of one of our projects, which is focused on developing a digital twin for a wastewater treatment plant that we are calling right now in this era water resource recovery facilities in the Netherlands. So the Eindhoven treatment plant. So we are partnered in this project with Waterschap de Dommel, which is managing and operating this plant, and also DHI, which are a software provider for modeling and simulation of wastewater treatment plants. So let's just a brief introduction on what a digital twin is. So we have usually our physical systems, which in this case is a wastewater treatment plant, so a water resource recovery facilities. And you see like a typical conventional biological phosphorus, nitrogen, and COD removal with anaerobic and aerobic stage. So a typical system that we want to monitor and we want to optimize, let's say, the performance of this treatment plant. So what historically has been done is developing mathematical models for these type of systems and using that for optimization and decision making. So in this case, we are collecting historical data of the plant. We develop our models based on those historical data, calibrate and validate our models, and then use it for optimization purposes. Some people call this a digital shadow, which so the main idea is that it is not in real time. So it's just based on historical data. We use it to study and understand the system, improve our decision-making procedure with the physical system, and that's it. But then with the idea of digital twin, we want to move towards a real-time operation. So we want this digital replica of the system to be run and simulate the system in real time with real-time data. And then this gives us the opportunity to also give back real-time feedback from the model to the system to control the system in a better way. So in this case, we can actually go toward a proactive control system, which is where we see what happens in some hypothetical situations in the future. So we have like a prediction horizon with our digital twin that helps us to act proactively when something bad is going to happen in the system instead of waiting for that to happen and then react to that challenge or problem. So for the case of Eindhoven, that we have now a fully, let's say, running up and running digital twin for this system, I'm going to just show the basic and main components of this digital twin for this system. So we have obviously raw data that is being collected at the treatment plant, and they are being stored at the local databases at the plant. So the first step is that we want to validate this data. So we want to be sure that the quality of the data is enough for our modeling purposes. And that is the first and maybe the most important aspects of digital twin, is to be sure that the data is of high quality. So we have a data cleaning and pre-processing procedure and workflow in place that makes sure that the data is valid and of high quality. Then we have the dynamic model on the back of this system. So the data is actually being pushed to a cloud server. So in this case, a Microsoft Azure system cloud. And then we have the dynamic model, which takes this data, run in real time, and runs the simulation for us to predict the performance, the state of the system in real time. So what is, for example, the concentration of the dissolved oxygen in the aeration tank? And then obviously all of the output of this model also are stored back in the cloud. And then a visualization and user interface is in place where the end users, which in this case can be the operators of the plant or the managers or the engineers that are process engineers that are working at the plant, they can see in real time what is the status of the system and just interact with this visualization and user interface to like run different scenarios and etc. So in this case, we as BIOMATH are focusing on the first two aspects, so the data cleaning and pre-processing part and also the dynamic model, because these are the two important aspects in a sense that we need high quality data and a model that has a sufficient predictive power to be sure that everything that is in the visualization and user interface at the end is reliable actually for the operators to use. So first on the first aspect, so the data cleaning and pre-processing. So usually we have raw data, but in a lot of cases, depending on the nature of the parameter, which is, for example, flow rate or concentration of the ammonia, or phosphate, etc., we can have different problems in the data, some missing gaps, noises, outliers, and etc. So the data, the raw data usually needs some pre-processing to be able to get the valid data points in all timestamps to be sure that it can be used by the models. So we have different filtering, for example, algorithms that will be applied to this raw data sets in order to first detect the problems that we have, like missing points, noises, sensor faults, etc., and also some algorithms to deal with that. So how we can actually now replace those invalid points, either by, for example, interpolation, or we have like influent model and data-driven model in this case that can be used to fill some of the gaps of or the invalid points in the data set. So at the end, we want to be sure that the end data set, it's going to be reusable and reliable for the model. And all of this procedure should be in real time and should be automated. So we don't do this manually. We need to be sure that at each timestamp, we have a real-time data coming, and then which is the raw data, but automatically we get a data set at the end, which is reliable for the model. So in this case, for example, we have different data sets. Some data are being used actually for running the model as the input of the model. We call it the simulation, like the influent concentration, for example, temperature of the process, and etc. Some of the data we are using for validation purposes. So we are, for example, using the DO concentration in the aeration tanks to be sure that the model actually predicts that value well. So they are not used as the model input, but as the validation. And obviously, we have also started to collect the settings of the controllers in the system to be sure that we are keeping track of every operational settings in the system. So we can be sure that if, for example, a set point of a controller has been changed, at what time and exactly when did that happen. And this is like an every 2-hour procedure. So every 2 hours, a new batch of fresh validated data will be pushed to the cloud to be used by the model. So in the next step, we have the dynamic model, which is running in the back of this system to predict the state of the system. So in this case, what is important is usually the dynamic model of wastewater treatment processes are modeled and described with the tank in series concept in mind. So this means that we, in order to actually mimic the hydraulic behavior of the system, of the tanks, the bioreactors, we are modeling them as a number of tanks that are connected in series. This is a very, very simplistic assumption for the hydraulic of the system. And in the large systems where we have a lot of mixing problems, for example, this is not a very good representative of the different concentration profiles within one tank. So that's the reason why we move towards the compartmental model of the plant. For that, so we use the CFD simulations, which are, as you see in the bottom, for example, in the aeration tank of this system, we run a CFD simulation and we see how the DO concentration is actually locally distributed in this tank. And by this knowledge that we get, so we see that, for example, the DO is not evenly distributed within the tank, we change the way that we model the aeration part of the system. For example, here, the blue tanks that you see in the graph in a better way. So we call this compartmental model. So these are now not connected in series, different compartments that they can actually have exchange flow rate between each other. This actually is a better representation of the reality of the system, which helps also in the calibration of the model. So it reduces a lot of unnecessary calibration effort. So in the case of Eindhoven, we have done it 2 times. So one for the aeration tank that you see based on the DO concentration profile, and the other time is in the anoxic tank based on the solid concentration. So this was also important for the prediction power of the model, because the effect of the RAS, so the return activated the sludge into the anoxic zone, is actually a huge impact on the TSS concentration profile. So all of this work has been done in order to improve the prediction power of the model to have a better prediction for example, DO profile or the nitrate profile and TSS profile in the system. So usually the tank in series concepts are very simple, so they have low computational costs, obviously, but they lack the details on the hydrodynamic of the systems. And if we have very highly dynamic systems, this is quite an issue. But for example, by not having very high variations in the data in the flows, this might not be an issue. So it's not that always we need to move towards a compartmental model, but for some specific cases, this is a crucial step. And then we use the compartmental model, which is slightly more complex than the TIS, but it's still not as much as, for example, the pure CFD models. And it's a lot faster than the CFDs, but it's still a bit maybe has more computational cost than the tanking series. But in the context of digital twins and the real-time operations, which is not like real-time in seconds, but we are talking about a couple of hours, for example, this is quite still affordable for the digital twin to go for a compartmental model that runs in real time. But the important aspect is that it actually reduces the effort on the calibration. So we don't go to overfitting the model for some parameters, but if we know that the source of those problems are not in those parameters, but are the representation of the hydrodynamics of the system. And finally, we have the user interface. That's so the results of all these efforts can be visualized. So some aspects that is important is that in this case, we actually see the simulation of the system in real time. As you can see, we have some simulations in the past, for example, a few hours based on the historical data, based on the past data from this point, and also a prediction horizon. For example, in this case, we can see that we have like a few hours of prediction horizon where we see where the future of the system will be in the next couple of hours. And we have defined also some KPIs to monitor the system, like, for example, the aeration energy, so the sludge age, the HRT of the system, and these things. So this gives really a nice opportunity for the operators to see the state of the system in real time and what can happen in the next few hours if something systematically or drastically changed in the system. For example, a pump, for example, fails in the system. So they can see that by that what happens in the next few hours. So relating to that, so we have two separate parts in this two separate interfaces, let's say, in this digital twin platform. One is called learning plant and one predictive plant. So by the learning plant, we want to learn about the system. This is mostly about the historical simulations. So from this point in time that we are the moment that we are in time now to the past, for example, past 6 hours, past couple of days, for example. And then we can run multiple scenarios based on those past values to learn about the system, that if in a situation, for example, a pump fails, what would be changed in the system apart from the thing that we have seen so far. And also we can have the forecast simulations. As I said, for the future prediction horizon, we can also run different scenarios to see what then will happen in the next few hours, for example, if a pump fails in this case. So this is the whole idea of the digital twin that can be used by the operators and is now up and running and are being used for training of the operators. And it's important to actually involve them also in this process. So one of the aspects that we need to consider for developing the digital twins are actually see how those end users are going to use this. So we want to be sure that the things that we are developing actually are relevant for them. So at the end, I want to conclude with some important points. So like, as I said, the digital twins are the future of proactive management and optimization. So compared to how we traditionally and conventionally use the models and have used the models in the past decades for the optimization of these systems, but the future is really going forward to more real-time operations. So the concept of digital twins in this case. And as I said, probably the most two important challenges in developing digital twins are first the data quality and the predictive power of the models. And data quality is quite a challenge in a lot of treatment plants. So Eindhoven is a, let's say, a luxury plant that they have a lot of data and sensors in place, but that is not the case in all of the systems. So having a data quality in real time, high quality data in real time, is quite crucial. So in this case, that is why that we also use that like the influence generators that I mentioned in the data pre-processing part. So data-driven models like the data-driven influence generators are also extremely valuable, especially in the cases that I mentioned for the treatment plants that are less monitored. So we have less data available, and we can use some data-driven models to actually provide us with the data set based on those limited available measurements that we have, for example. And then at the end, the compartmental model is also very powerful, especially for lowering the calibration need, which is also quite a challenge, because in a lot of cases the models are over fitted by over calibrating the parameters of the model, and that is not a, like, let's say, a good practice in model development, because then you might see, when you test the model for the other data sets that have not seen by the model before, you can actually reach to not reliable results, because you were focusing on some calibration parameters which were not the source of the problems, which in a lot of large treatment plants and bioreactors, hydrodynamics is the source of a lot of the problems in model calibration and validation. So that's it.